This week we're going to be working on a mixed design problem for proportioning ingredients for a concrete design. It'd be a really good idea to have Chapter 9 from the Portland Cement Association book either on screen or printed out in front of you. I do have the necessary tables and figures, screen captures of them in this presentation, but it might be helpful for you to have them in front of you so you can mark them up and work with them at your convenience. So the objectives of mixed design are really two things. We want to satisfy the design requirements for our concrete, and we want to make it economical. And by the design requirements, we're talking about the compressive strength, which is the primary property people attribute to concrete, right? How strong is it going to be? But more and more common are porosity and aesthetics, right? Architects are finding they can use concrete in a lot of different ways with colors and textures and patterns to make really, really nice looking finished products. And engineers are finding that they can use concrete as a draining material. So this example over here, this was a parking lot that we worked on, and you can see it's a very, very porous concrete. It's specifically intended to allow water to drain through it and basically eliminates surface water runoff generation from things like parking lots. Montana was really hesitant to adopt porous concrete. There's been a couple really, really good projects that have been studied in Billings and also in Helena, and they're proving to hold up really, really well in this climate. They're working wonderfully. You do have to run kind of a vacuum over these things every couple years to vacuum out the sand and the silt that builds up and gain that porosity back. But anymore, that's becoming a very important property of concrete that people are writing into the specifications. And then in the economic side, you want to use the available products that you have. So we know we need to use coarse aggregate, fine aggregates, and cement. Montana's really lucky. We've got great gravel pits, we've got good sand availability, and we have some local cement production facilities. So we can make very good product locally here. Early proportioning methods were very crude. People would throw together 1 part cement to 2 parts sand to 3 parts gravel by volume, throw in enough water to get it to stick together, and presto, you'd have concrete. But today's mixed design is becoming a lot more scientific, and it accounts for those desired properties: the strength, the durability, and the workability. Those are the 3 biggies. And then the aesthetics, which is becoming more and more common. And mixed design also accounts for the recipe variables. So we have aggregates. We have aggregates that we can work with. We have a water to cement ratio. We have entrained air, which is the air that we want to end up in our concrete. And then we have admixtures at our disposal to help modify those strength, durability, and workability properties. So compressive strength is, again, it's what most people attribute to concrete. It's how much force can that concrete withstand before it fails. And we measure it in PSI, pounds per square inch, right? It's how many pounds can every surface inch of that concrete withstand without failing. F sub CR, the required compressive strength, is basically your specified compressive strength plus some sort of safety factor. And that safety factor is based on either prior tests done on a recipe, so you know exactly what this recipe will achieve, or it's done on charts. Charts are a lot more generous. They build in a higher safety factor because you don't have experience with this recipe. You don't know what this concrete is going to achieve. These safety factors are real common, like in architecture, right? Architects, when they're designing roof structures, if you're in an environment that can expect 40 inches of snow load a year, you add in a safety factor of 2, and you design a roof to withstand 80 inches of snow, right? Same thing with concrete. You build in a safety factor to ensure your project won't fail. So we're going to go through a mixed design example. This is out of Chapter 9 in that Designing and Proportioning Normal Concrete Mixtures chapter of the PCA book. It's very similar to example number 2 on page 163. I did change one little specification so that we can use one of the tables slightly differently, but for all intents and purposes, we're working through example number 2. And keep in mind that these calculations that we're going to be working through are based on a theoretical 1 cubic yard batch. Right? When you see a concrete mix truck go down the road, that's typically an 8-yard truck. I think there's some big ones that can hold 10 yards. Concrete's ordered in yards on a job site. For our purposes in labs, when we're working on testing it, we batch down. So we go down to 1 cubic foot, or more commonly, even a half of a cubic foot. So when we get these final numbers at the end of our mixed design, we'll talk about batching up or batching down based on the specific use. So the project specifications, we're dealing with a 12-inch thick slab. We're going to say it has a 3-inch minimum requirement for cover over the rebar. There's a 4-inch minimum rebar spacing. The slab will be exposed to severe freeze-thaw conditions. It has a compressive strength specification of 3,500 psi, and there's no slump specified for the concrete that's going to be delivered on site. The material specifications, the raw materials that we have to work with, we're using a type 1 normal cement, Portland cement. I should be specific in that. Remember, cement is a generic term that means any kind of binding agent. We're working with a Portland cement mix design here. And Portland cement has a relative density of 3.15. Our coarse aggregate sample, or source, is a 3/4 inch minus gravel. And remember, 3/4 inch minus means that 3/4 inch is the largest size of the gravel particles in your graded gravel sample. It has a relative density of 2.68. It has an absorption of 0.5%, which, remember, that just means that's the moisture content when it's in its SSD condition. It's outside and exposed to the elements, and it currently has a water content of 2%, and its bulk density is 100 pounds per cubic foot. So that means if you poured this coarse aggregate into a cubic foot bucket, it would weigh about 100 pounds. The fine aggregate source is a natural sand with a relative density of 2.64. It has an absorption of 0.7%, which again is the moisture content when it's in its SSD condition. It's outside and exposed to the elements and has a water content of 6%. And the sand has a fineness modulus of 2.80. I had you do a homework example last week on fineness modulus. That's just a variable that you can calculate from a set of gradation results based on the summation of percents retained on specific sieve sizes on a sands gradation. So there's about 14 or 15 steps to work through a mix design. We're going to go through these one by one, and I'm going to refer to the appropriate tables and figures out of that Chapter 9. So step 1 is basically determining your safety factor. If we have a compressive force of 3,500 psi, we can get our safety factor from either Table 9-10 on page 158 or Table 9-11. If you have statistical data on prior mixes of this recipe, if you've done this recipe and you've tested cylinders and you know what kind of compressive strength you can expect to achieve out of it, you can use Table 9-10. We don't have any statistical data, so we're going to go to Table 9-11, which basically just gives us a very generous safety factor that we increase our PSI by. So we have 3,500 PSI. We come over here to the 3,000 to 5,000 range, and it says basically we're going to add 1,200 for our required compressive strength. So 1,200 is what we're adding, so 3,500 PSI plus 1,200 means we're going to be actually designing for 4,700 PSI concrete to guarantee that we'll achieve our 3,500 in conditions after it's released to the public. Step 2 is to determine the water-cement ratio. And you can determine this two different ways. We do get the exact same results, so I'll just show you really quickly both ways. The first way is figure 9-2 on page 151. And we have two scales here. We have a metric scale on the left and our English units scale, PSI, on the right. So we said we're needing 4,700 PSI, so we come up here to 4. These are units of 1,000 psi, so 4,000, here's about 4,700 psi. We're going to come straight over to either the non-air-entrained concrete or the air-entrained concrete. And this project, right, we said was exposed to freeze-thaw conditions, so it does need to be air-entrained. In Montana, the only time you're dealing with non-air-entrained concrete is if you have an indoor application. Almost all concrete delivered in Montana will be air-entrained. So we come over to that line, we come straight down, and we read on the scale at the bottom approximately 0.42, and that's the water-to-cement ratio. We could also get that from Table 9-3 up here. They're showing us at 4,000 psi. Over here in the air-entrained concrete, you would have a water-cement ratio of 0.48, and at 5,000 psi, you would have 0.40. So we would have to interpolate between those two data points to determine where we are in between along that scale. And I just do that down here at the bottom. If we have 5,000 to 4,000, that's basically 10 units of 100. We're 300 units away along our scale, so that's where I get 3/10 from. So we're going to proportion 3/10 of the way along a scale that goes from 0.4 over to 0.48. So I call that position along that scale x, and x is going to equal 3/10 times the maximum and minimum ranges of that scale, and that's basically going to give us this value right here. And then we're just going to simply add that from the end of the scale that we're working from. So 3/10 times 0.08 is 0.02. We add that to where we're starting, 0.4, and we would come up with 0.42 as well. We need to go to Table 9-1 to ensure that we're not exceeding a maximum allowed water-to-cement ratio. We determined 0.42. According to Table 9-1, which you can find on page 150, you have columns here that represent water-to-cement ratios, maximum allowed, and then the rows over here represent exposure conditions. we said we were going to be exposed to severe freeze-thaw conditions. So we come over in that row to our water-cement ratio column, and you can see we're allowed a maximum of 0.45. Well, that's good because we're not exceeding that. We're only at 0.42. 0.42 is a more conservative value. It's lower, so that's what governs, and that's what we're going to use. You would use the lower of what you determined on the prior table against what you determined on this table. Step 3 is to determine whether or not your coarse aggregate is appropriate to use based on the rebar spacing. So a couple rules of thumb here. Coarse aggregate may not exceed 1/5 of the narrowest dimension between the sides of forms. So if you're setting up forms for a foundation wall, your aggregate cannot be more than 20% wider than that narrow dimension. Coarse aggregate may not exceed 3/4 of the clear space between rebars. Or if there's no rebar, so in unreinforced slabs, the aggregate size should not exceed 1/3 of the slab thickness. So you can recall from our project specs, our project is calling for a 4-inch rebar spacing, which means we're allowed to be up to 3/4 of the space between rebar. So we could be 3 inches big. That's a really, really big piece of aggregate. You would only find that on something, between an interstate and an airport runway. Our specified gravel of 3/4 inch minus doesn't exceed that restriction, so we're allowed to stick with it and use it. Step 4 is to determine the required air content. And we're going to go to table 9-5 on page 154. And you have these columns here for your aggregate sizes. The top half of your table is for non-air entrained concrete. We're going to use the bottom half of the table, which is air entrained concrete. And you have exposure conditions over here. We're severe exposure, so we're going to come over on severe exposure into the 3/4 inch column, and you can see we're at 6.0. And that means 6% is the desired air content of our concrete to give us the durability needed for those exposure conditions. You can see this note down here that I have circled in green. The air content and job specifications should be specified to be delivered within -1 to +2 percentage points of the target value. So what that means is a batch plant can deliver their concrete on site within a 3 percentage point range of the desired target. -1 to +2. So if we're specifying 6, it can arrive on site 5 to 8. Right? Well, we don't want 5. 5 is going to reduce the durability and jeopardize the longevity of that concrete. So if we want to guarantee that we get 6, but we know the contractor is allowed to deliver it 1% low, that's why I say down here at the bottom, we want to ask for 7. That way we're guaranteed 6 that arrives on site. Step 5 is just to look at your slump specifications. We don't have any slumps specified for this job. Therefore, we'll use the recommended range from table 9-6. 9-6 is on page 155. And you can see down here in the row for pavements and slabs, which is what we are, we have a maximum slump of 3 inches, a minimum slump of 1 inch. So we're going to use a 3-inch slump in the following steps for our proportioning purposes. And I know we haven't talked about slump yet, but that's one of the quality control tests. It basically measures the workability of concrete that comes on site. Step 6 is we're going to determine the water requirements for this mix design recipe. And we're going to go back to table 9-5 on page 154. We're still in our 3/4 inch aggregate column, but now we're going to use these values up here, and these are your slump ranges. So we just said that we're going to deal with a 3-inch slump. So we're going to come over at 3 inches into the 3/4 inch aggregate column, again down here in the air entrained portion of this table, and you can see the value of a 305. And look at the title of this table. This is water in pounds per cubic yard of concrete. So we need 305 pounds of water in our theoretical yard mix design. Step 7 then is to determine the cement content. And from one of those earlier steps, I think step 2, we said we needed a 0.42 water to cement ratio to give us 4,700 psi concrete. Well, in the last step, we just determined we needed 305 pounds of water in our cubic yard of concrete. So we're just going to set up a simple ratio to solve for cement. Water to cement ratio just means water over cement has to equal 0.42. Sorry about that, I had a little freeze up there. Water over cement has to equal 0.42. Or we could rewrite that expression algebraically so that cement is equal to water over 0.42. We know water is 305 pounds per cubic yard. If we divide that by 0.42, we need 726 pounds of cement in order to maintain the proper water to cement ratio for 4,700 psi concrete. Step 8 is to determine our coarse aggregate content. We're going to go to table 9-4 on page 152. And this is where the fineness modulus of your sand comes into play. You have these 4 columns here, all for a different fineness modulus. So our fineness modulus was 2.80. We're going to come over here to our 3/4 inch aggregate row, and when we intersect that, we get a value of 0.62. And again, look at the title of this table. This is the bulk volume of dry rotted coarse aggregate per unit volume of concrete. So that means 62%, right? 0.62 is 62% of our cubic yard of concrete by volume has to be occupied by coarse aggregate. We can't easily measure volume, right? We can easily measure mass. So we're going to continue this step and use that familiar relationship, density equals mass over volume, right? If we know the volume has to be 0.62, we can solve for the mass. So we simply rewrite that as mass equals density times volume. So mass equals 100 pounds per cubic foot was the density of our aggregate. That was given in the material specifications back at the beginning, right? Times volume. Volume, this is our theoretical 1 cubic yard of concrete. We're mixing units here though, right? We've got 100 pounds per cubic foot, but our total mix design is per cubic yard. So we want to convert cubic yards into cubic feet, and we do that by multiplying it by 27, basically. There's 27 cubic feet for every 1 cubic yard. And when we multiply that out, the mass of an entire cubic yard of aggregate would be 2,700 pounds. But from the last screen we just looked at, we needed 62% of our cubic yard of to be occupied by coarse aggregate for our concrete mix. So we take our 2,700 pounds per cubic yard, times that by 0.62, and that tells us we need 1,674 pounds of gravel for every cubic yard of concrete that we're going to be mixing. Step 9 is to address the admixture requirements. And admixtures are chemicals to help achieve those properties, right? And next week is when we focus on admixtures. But those specifications will come from the chemical manufacturer. The only admixture we're using in this concrete is an air entrainer so that we can achieve that desired 7% air content from the earlier step. We're just going to have to make an assumption right now and assume that the manufacturer recommends 0.9 fluid ounces per 100 pounds of cement. So we set up a simple calculation, 0.9 fluid ounces per 100 pounds of cement. We multiply that by the number of pounds of cement per cubic yard of concrete that we determined from an earlier step, and we would need 6.5 fluid ounces for every cubic yard of concrete being produced. Step 10 now is to determine the fine aggregates needed for the mix design. And this is probably the longest step, so there's a number of slides that go with step 10. So far we've calculated the following in our theoretical cubic yard, right? We're going to be adding in 305 pounds of water to 726 pounds of cement, 1,674 pounds of coarse aggregate, and 7% of that cubic yard is going to have to be occupied by air, right? Entrained air. So what we want to do is convert these masses into volumes so we know how much space of our theoretical cubic yard is already occupied. Whatever space is left is space that's going to be filled up with sand, right? Fine aggregates. So again, we go back to that familiar relationship, density equals mass over volume. We're going to convert these masses now into volumes and kind of work backwards. So if density equals mass over volume, and we want volume, we can rewrite that volume equals mass over density. And remember, even back to the soils class, density is equal to the relative density of any material times the density of water. Remember, because relative density tells us how many times heavier something is than water. Because we're working in pounds and cubic feet, we could extend that out then to say that the density is equal to relative density times 62.4 pounds per cubic foot, because that's the density of water in these units. So the volume of water then is equal to mass of water over density of water, which is 305 divided by 62.4, or 4.88 cubic feet. The volume of cement is equal to mass of cement divided by density of cement, which is 726 pounds divided by relative density of cement, 3.15, times density of water, 62.4, and you get 3.69 cubic feet. And the volume of our coarse aggregate is mass of coarse aggregate divided by density of coarse aggregate. That's 1,674 pounds of aggregate divided by relative density of those aggregates, 2.68, times density of water, 62.4, gives us 10.01 cubic feet of space occupied by the coarse aggregate particles. The air also takes up volume. It has no mass, but it does have volume. And 7% of our cubic yard had to be occupied by air. So 7% divided by 100 gets you into decimal form. And again, we wanted to express all of these volumes in terms of cubic feet to be consistent. So we convert cubic yards into cubic feet by multiplying by 27, and 1.89 cubic feet of our theoretical cubic yard is occupied by nothing but air. Intentional air, right? Entrained air, not rock pockets. So the summary of the volumes then that we just computed, the water takes up 4.88 cubic feet, the cement takes up 3.69 cubic feet, the coarse aggregate takes up 10.01 cubic feet, and the air takes up 1.89 cubic feet. So out of our cubic yard available, we're already occupying 20.47 cubic feet. There's 27 total cubic feet available in a cubic yard. We subtract out what's already occupied, and that leaves 6.53 cubic feet available that has to be occupied by our fine aggregates now, our sand. So we're going to go back to that familiar relationship, density equals mass over volume, and convert this volume now back into a mass. So density equals mass over volume. Now we want to solve for mass. So mass equals density times volume. And again, density is equal to the relative density of that material we're working with times density of water, or relative density of our fines times 62.4. So the mass of the fine aggregates is equal to 2.64, which is the relative density, times 62.4, density of water, times the volume, which is 6.53 cubic feet, and that would yield 1,075 pounds of fine aggregate. So the summary now is 305 pounds of water, 726 pounds of cement, 1,674 pounds of coarse aggregate, 1,075 pounds of fine aggregate, and 6.5 fluid ounces of admixture. All of that together will yield 1 cubic yard of concrete. And that means we're done, right? Because those are the only ingredients that we have to work with in our mix design. Well, unfortunately, wrong. If you remember to a couple of lectures ago, we talked about moisture conditions of aggregates and how that saturated surface dry condition was the ideal condition for an aggregate when included in a concrete mix design, because that means the aggregate will not be stealing any water from the cement, nor will it be contributing excess water into the recipe design. Okay, I apologize again. I had another little freeze up there. I can't go back to the prior screen, but that was just a screen that showed the different moisture conditions of the aggregate particles from dry to wet. We have to account for the moisture conditions of the materials that are being used, and those moisture conditions were given in the material specifications at the very beginning. So we will need to adjust those final mix design weights that we just looked at. If you're a little unsure of where we're at, now would be a really good time to just kind of pause things, go back, rework this example, or follow this example again from the beginning before we do these last couple steps of accounting for the moisture conditions. I'd really like you to be confident in knowing how we got to the point where we're specifying the weights of all these individual ingredients. Some of those steps required us to work between volumes and masses, but that should be starting to get very easy for you working through that density relationship. Okay, remember, absorption was the water content of the particle when it was in its saturated surface dry condition, and Typical absorption values for coarse are 0.2 to 4%. Typical for sands are 0.2 to 2%. So what we want to do is account for that moisture content based on the absorption value given in the material specifications of our coarse and fine, and also the current moisture content given in the material specifications of the coarse and fine aggregates. So step 11 is we're going to adjust the dry weights of our aggregates. And from the material specifications, remember water content of our coarse was currently 2%, and the water content of our fines was currently 6%. So because they're a little wet, when we weigh out the required masses, those required pounds to add into our cubic yard, some of that weight is going to be water. That's not aggregate, right? We need the aggregates to give us the strength of our concrete. So when we calculated prior that we needed 1,674 pounds of coarse aggregate, we don't want some of that requirement to be made up of water. So we need to adjust these dry weights to account for the water, such that when we weigh out wet rocks, we know we're going to be receiving 1,674 pounds of mineral particle in that mass. So the calculation is the adjusted weight is equal to the dry weight needed times 1 plus the current water content. For coarse aggregates, we need 1,674 pounds of dry rocks. We're going to multiply that by 1 plus the current water content, which means we need to weigh out 1,707 pounds of these moist aggregates to guarantee we're getting 1,674 pounds of equivalent dry rocks. Same thing with our fines. We need 1,075 pounds of dry sand. We multiply that by 1 plus the current moisture content of our sand, so we actually need to weigh out 1,140 pounds of the moist sand to guarantee that we're getting 1,075 pounds of actual dry sand. Step 12 is to calculate the contributed water from those aggregates. And so back to the material specifications, the water content, like we just looked at, of the coarse aggregates was 2%, and the absorption value for those coarse aggregates was 0.5%. The water content of the fines was 6%, and the absorption value of those fines is 0.7%. So for both of these conditions here, the current moisture content is higher than the absorption value. So think about what that means to the aggregate. Is the aggregate closer to the dry side of SSD, or is it on the wet side of SSD? Only if those two numbers were equal would the aggregate be in an SSD condition. So because our moisture content is higher, these are wet rocks. These are actually going to be contributing excess water that we don't want in our concrete mix design. And we can quantify that. The contributed water is equal to the dry weight times water content minus absorption. So we're going to calculate that for both. Coarse aggregates is equal to the dry weight, 1,674 pounds, times water content, 2%, minus absorption, 0.5%. Make sure you put those in number form, take them out of percentage form, and that'll tell us we're getting 25 pounds of waters coming along for the ride that we don't really want. Fine aggregates, 1,075 pounds of dry mass times moisture content of 6% minus absorption of 0.7%. Again, put those into numbers, take them out of percentage form, And you're going to get that sand, because it's considerably wetter, is contributing an additional 57 pounds of water. Now, contributed water doesn't have to be a positive value, right? And I put that here in this red note. You can end up with a negative number here. If the current moisture content of your rock was 0, right, so if it was oven dry, if it was bone dry, but it had an absorption value of 0.5%, it's going to act like a sponge, right? It's not going to be contributing water. It's going to be stealing water. So as long as you maintain your equation in this proper form and follow your signs, you would get a negative number here. And that means you're contributing a negative water, which means you actually have to add more water in the next step. So don't let a negative number screw you up here. Pay attention to your signs and understand what these values are telling you. And that just means using common sense when you look at the moisture content values of the aggregates being used. So then step 13 is to adjust the water requirements. So the final water requirement is equal to the original water requirement minus the aggregate contributions that we just calculated. We originally needed 305 pounds of water. We're going to subtract out the coarse aggregate contribution, and we're going to subtract out the fine aggregate contribution, which is 305 minus a positive 25 and minus a positive 57. Right? Both of those aggregates had excess water, so we need to subtract that out of our water requirements. And that's where I said if you had a negative value and your dry rock was going to steal water, you would actually be subtracting a negative or increasing the water requirements. So just pay attention to your signs. You know, it's not rocket science, it's concrete science. You're going to hear Keith Oates use that joke a lot when we have him visit from Montana Contractors Association. So the adjusted water requirement is now 223 pounds of water that we need to add because our rocks are bringing in a lot more for the party. Total, they'll give us 305. Step 14 is the final mixed proportions. Our new water that we're adding is 223 pounds. We still have our 726 pounds of cement. We're weighing out 1,707 pounds of coarse aggregate. We're weighing out 1,140 pounds of fine aggregate. And again, remember, these are adjusted weights because we're weighing them out in a wet condition. And our admixture is still 6.5 fluid ounces. And if you add all of those together, you'll yield 1 cubic yard of concrete. To scale this batch down for cubic feet, you want to multiply each weight by x over 27, where x represents the number of cubic feet desired. So the typical batch size I ask us to mix in class for testing purposes is 1/2 of a cubic foot. So to produce a 1/2 a cubic foot trial batch, we would want to multiply each weight by 0.5 over 27, that ratio. So step 15, the last step here, scaling the proportions down for a trial batch. If we wanted to produce a 1/2 of a cubic foot, we would scale our water down to 4.13 pounds, our cement down to 13.44 pounds, our aggregate gets down to 31.61 pounds, and our sand, our fine aggregate, gets scaled down to 21.11 pounds. And even our admixture would get proportionately scaled down to 0.12 fluid ounces. When you get that small with fluids, it's probably easier to measure in millimeters, or milliliters, I should say. And then just one last kind of common sense check on yourself. You know, the approximate density of concrete is around 150 pounds per cubic foot. Use that rule of thumb to check your work. A 1/2 of a cubic foot batch then should be half of 150, right? Or around 75 pounds. And if we add up all of these values that we just came up with, it adds up to 70.29 pounds. It's in the ballpark. It's not likely that we have any gross errors in our mix design.